Swayam Prabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Process Technology Part 1 Module 41. In the last lecture we had talked about numerically designing a case where we had known values of the measured forces as well as the geometrical parameters. Based on that we estimated what is going to be the ultimate shear stress of the material in the cutting zone. Let us actually reverse that cycle and try to estimate from material properties and geometric parameters given what is going to be the cutting forces, okay, in the following example. So we have one example here which talks about a mild steel piece being machined at a cutting speed of about 200 meter per minute, and this being done with a tool rake angle of 10 degrees. That means with respect to the vertical, the tool rake face is at 10 degrees. The width of cut and the uncut thickness are given to be 2 mm and 0.2 mm respectively, and the average value of the coefficient of friction, and now we are just taking this to be average value, although the presumption of taking an average value is not completely true, because due to the unequal distribution of pressure of the chip on the rake face, there may be a change in the normal force that it receives and from the tool face, thereby resulting in differential friction, okay. And also the coefficient friction changes with respect to temperature as the cutting process happens. So but we are right now assuming this to be uniform, an average value reported of 0.5, and the shear stress tau s of the workpiece is now it's a material property. Again, we want to consider it to be time invariant, although it is not completely true, because shear stress also sometimes depends on the temperature of the cutting zone. So here in this case we treat that to be temperature independent and as 400 Newton per meter square. So we need to determine what is phi, the shear angle in this particular case, and we also need to determine what is the cutting and thrust component of the machining forces. So using the Merchant's first solution, let us actually assume that we are using the first solution for our calculations here. We already know that 2 phi plus lambda minus alpha is equal to 90 degrees. Alpha here is given as 10 degrees. The friction angle lambda can be calculated as tan inverse of average mu, which is actually equal to tan inverse 0.5, about 26.57 degrees. Having said that, we have now the phi value recorded as 90 plus 10 minus 26.57 by 2, 36.7 degrees, and the Fs value or the shear force value here recorded as Wt1 tau s by sin phi, as I had illustrated earlier, this being the total shear plane area, and this is actually equal to the ultimate yield strength of the material in shear. So it is already given to be a constant value 400 Newton per millimeter square in the problem example. So we want to put this value of the width, which is 2 mm, times of the uncut chip thickness, which in this case is 0.2 mm, so 0.2, times of tau s, which is 400 Newton per millimeter square, divided by sine of phi, so sine of 36.7 degrees. So in this case the Fs would come out to be, or the shear force would come out to be close to about 262.3 Newton. And the way we calculate from the shear force the various components Fc and Ft, so you already know that the resultant force times of cos of phi plus lambda minus alpha from the Merchant circle diagram represents a shear force. So in this case obviously then the resultant of the shear and the normal forces in the shear zone, or the similar to the resultant of the frictional and the normal reaction of the tool face on the chip. So that is going to be equal to 262.3, this Fs value, divided by cos of phi, which is 36.7, plus lambda, again 26.57, minus alpha, which is 10 degrees. Okay, so this whole thing corresponds to about 438.6 newtons, which is reaction force or resultant force R, and you can calculate Fc and Ft by putting the R component and Fc is defined as r cos lambda minus alpha. I think we have illustrated this earlier in the merchant circle. So this becomes equal to 438.6 times of cos of 26.57 minus 10 degrees, 420 Newton, and Ft becomes equal to r sine of lambda minus alpha, which is 438.6 sine of 26.57 degrees minus 10 degrees, which is equal to 125 Newton. So that is how you calculate the cutting force as well as the tangential force to the direction of cut. So in a nutshell, you can now estimate from the material properties and the geometrical property the normal forces and the cutting forces in the tooling zone or the cutting zone. And in the earlier example, we had done the reverse way by looking at the measured cutting and tangential forces, what is going to be the the final shear, ultimate shear strength. So having said that, I think we have covered more or less everything that is needed to understand merchant theory properly. We now need to go to a little bit different aspect about calculating the specific cutting energy of the material, and for that let us assume that if Fc is the cutting force when a machining is done, let us say at a velocity v, the total power consumption, I think we had earlier discussed, comes out to be the force velocity product, right. So it is basically Fc into v that is used to define the power. At the same time, if T1 and W are the uncut thickness and the cutting zone width, the volume of the material removed per unit time is then obviously WT1V, right. So this is basically the total volume or total sectional area of the material, and V is the velocity, and so that is going to be the total amount of volume per unit time that is being removed. Okay. Now what happens to the deformation process, or how the chip gets deformed and rises or rides on the rake face is a different question, but the amount of volume that you are flying out as chip is typically the volume that you are shaving off the material, right. So in this case, this is the, if I assume V to be in a direction perpendicular, in the cutting direction, so cutting velocity. So obviously cutting velocity times WT1 should be able to give the sufficient volume per unit time removal, which would result in again deforming and riding on the tool face and formulating into a chip. Okay. So having said that, the energy consumption per unit volume rate of material removal, okay, which we commonly also know as the specific cutting energy or specific energy, is then given by UC equals FCV, which is the amount of energy consumed per unit time, divided by the volume rate of removal per unit time, which is WT1V, or in other words it is FC divided by WT1. So this 1 by WT1 factor is really pretty important and it gives you a relationship between the cutting force and the specific energy that is being spent in order to remove a certain material at a certain volume rate of removal. Therefore, I can probably say that the amount of energy that is needed per unit time, or the amount of cutting power that is needed, represented by W, can be represented as UCQ, where UC is the specific energy of the material and Q is the volume rate of removal, that is how many millimeters cube per minute or per second is being removed of the material. So, Q is the volume rate of removal, and this UC is basically again the power spent per unit volume rate of removal. So, multiplying that with the volume rate of removal would actually give you the total power that is needed for cutting the system, or performing the whole cutting process. So, this specific energy is a very convenient basis for judging the power required for a given process. If I say that the specific energy related to a volume, a certain volume rate of removal is higher, or for a certain process is higher, it means that you can basically you would like to consume more amount of power to remove material in that particular system. If the specific energy is lower of a certain system, then you have to use less power in order to cut more material of the system. So, an examination of the various literature data suggests that you can relate this UC to the uncut chip thickness T1 through a relation U0 T1 to the power of minus 0.4, where, and this is again completely a sort of a correlational formula. So, where this T1 is the magnitude of the uncut chip thickness of the cutting process, okay, and this is measured because it's a kind of a regressional formula. This T1 actually is measured in millimeters. So, in this particular relationship, the T1 is in millimeters, and the value of U0 really depends on the materials. So, obviously, we are splitting down the UC into two components. One is a material related property and another which is actually related to the thickness of the cut that you are exercising. So, at one particular round of cutting, how much material or how much depth you are giving in terms of uncut chip thickness is also critical to determination of the rate of consumption of energy which would be needed to remove that material. So, therefore, we are trying to split it up into a material property U0 and thickness T1 to the power of minus 0.4. So, having said that, the value of UC can be substituted in the relationship which we developed here, right here, and we can say that UC, which is actually equal to FC by WT1 as found out before, is nothing but U0 T1 to the power of minus 0.4, and basically FC therefore becomes equal to WT1 times of U0 T1 to the power of minus 0.4 joule per millimeter. This joule can be corresponding to Newton meter. You could actually represent this by changing this to 1000 Newton millimeter, and I can write this down as 1000 WT1 U0 T1 to the power of minus 0.4 Newton. Okay. So, that is how you can actually find out the cutting force requirements given material property U0 of particular material, that is what is the specific energy of the material, and also the width and the depth of the cutting zone. So, this is very important to determine how much force would be necessary and sufficient to start removing the material. So, let us do a numerical problem example to find out how we apply the specific energy concept in the cutting. So, let us say we have a case where we need to find out the order of magnitude of the cutting component of the machining force during the orthogonal machining of mild steel with an uncut chip thickness of 0.25 millimeters and a width of the cut W being equal to 2.5 millimeters. So, we already know that the U0, which is a material specific property, assuming this to be a mild steel, as I already told you here, component, the U0 for mild steel is recorded as 1.4 joule per millimeter cube. So, having said that, the amount of cutting force Fc equals 1000 times of the value of the uncut chip thickness, which is 0.25 millimeters, times of the width of the cutting zone W, times of 1.4 the U0 value for mild steel, specific cutting energy for mild steel, times of T1 the uncut chip thickness to the power of minus 0.4, which is again represented here 0.25 to the power of minus 0.4 Newton. So, this becomes equal to 3500 times of 0.25 to the power of 0.6 Newton, which is 1517 Newton. So, this is the kind of force requirement which is there for starting to cut on this mild steel sample. To compare this Fc value, which is predicted in the, or which is calculated in the last step here, with respect to, let us say, something to the estimated force of cutting from using one of the criteria which we illustrated earlier. Let us say we use the Lien-Schaffer's criteria, which talks about phi equal to pi by 4 plus alpha minus lambda, okay, tan inverse mu. So, we can probably find out whether we are still in the range of, whatever is estimated by the specific energy method, at least order of magnitude wise are the force values same. So, in this case, let us assume that alpha equal to 0 degree, a rake angle of a tool which is almost vertical, mu some of the parameters we have assumed earlier as 0.5, and the phi calculated from the Lee-Schaffer's condition, which is 45 degrees plus 0 minus tan inverse of 0.5, which is actually 26.54 degrees, and this becomes equal to 18.43 degrees. So, the Fc value here would be equal to obviously the width of cut times of the uncut chip thickness T1 times of times the ultimate shear strength in case of mild steel, which is 300 Newton per millimeter square, it is assumed to be that value, times of cos of lambda minus alpha, or cos lambda, okay, divided by sin phi times of cos phi plus lambda minus alpha. So, this value is basically cos of lambda, and because alpha is 0 in this particular case, as you have seen in the assumptions itself. So, cos of lambda, which actually becomes equal to cos of 26.57 degrees, okay, and right here is basically sin of phi, which is sin of 18.43 degrees, and cos of phi plus lambda minus alpha, which is actually equal to cos of 18.43 degrees plus 26.57 degrees minus 0. This becomes equal to roughly about 45 degrees. So, that much newtons would be the force Fc from normal Lee-Schaffer's criteria for optimization of power. So, we find out that the values are pretty specifically very close. Fc in this case comes out to be around 1000 newtons. If I just calculate by substituting the values of this cos 26.57 and all the other sin and cos parameters in the denominator, the total force of cut happens to be about 1000 newton, which is at least order of magnitude wise quite close to this 15-17 newtons. Okay. So, at least with both the methods we can predict similar orders of magnitude of the cutting force as illustrated here. Now, the other issue which I would probably like to take up in the next module would be related to the heat transfer process and related to the temperature rise in the cutting zone because of the cutting action. Obviously, there is a shear plane across which the chip is being deformed, and that all energy is stored in terms of increase in temperature or heat energy, and so there is going to be a tool temperature zone which comes up because of all this energy exchange. So, a part of the energy probably goes to the workpiece, a part is flying away with the chip, and the fly is retained by the a part of it is retained by the tool. So, in that manner we will try to model to see what is the heat flow and what is the temperature rise of all these three zones while doing a machining operation. As of now, in this particular module I would like to end it here. Thank you so much. Bye bye.